All right, let's get started. Hello, everyone, and welcome to another installment of the Interstellar Probe Study webinar series. My name is James Mastandrea, and I am the Deputy Study Manager for the Interstellar Probe Study. Thank you very much for tuning in to today's webinar. We have a wonderful presentation today on Into the Unknown Local Interstellar Cloud. And after the presentation, we will have a question and answer session. Before we start, I would like to outline the logistics of today's event. As a member of the audience, your audio and video are off. During the presentation, please submit your questions in the question and answer feature, and please indicate which panelist your question is for. You may also upvote questions. During the question and answer session, I will start with questions with the largest amount of upvotes and proceed down the list. Also, for more information about the Interstellar Probe Study and for information on future webinars, please visit the Interstellar Probe Study website. And now I'd like to introduce today's speakers. Elena Provornikova is a space physicist at the Johns Hopkins University Applied Physics Laboratory with research interests in the physics of the outer and inner heliosphere. She is the deputy PI on the Heliophysics Mission of Opportunity Sheila and is the lead scientist for heliophysics on the Interstellar Probe Study at APL. Seth Redfield is an associate professor at Wesleyan University. He is an observational astronomer who uses the largest ground-based telescopes and space observatories to study the gas and dust in our immediate interstellar surrounding and in the atmospheres of transiting exoplanets. He has served on the NSF Committee of Visitors, is an Aurora member representative, and has been a panelist on many NASA grant and mission selection committees. Rosine Lallement is the senior scientist at France's Scientific Research National Agency. Her research includes working on the solar wind and the solar wind interstellar medium interaction by means of remote sensing detection of the neutrals in and around the heliosphere, using data from various missions, for example, Voyager, PROGS, and SOHO, and in parallel by means of stellar spectroscopy from Hubble, the Extreme Ultraviolet Explorer, and ground-based observations. Furthermore, she has worked on the identification of the local cloud, estimated its density, the deceleration and deflection of the interstellar hydrogen at the heliopause crossing, and this has provided constraints on the size and shape of the heliosphere. And with that, Elena, the virtual floor is yours.
Thank you, James. And yes. So hi, everybody, and welcome. I would like to spend 5 minutes to give an introduction and tell you about the Interstellar Probe mission concept study, which is being led by APL with support of more than 250 scientists and engineers from 9 countries around the world. This is a trade study with pragmatic approach, looking at different scenarios of the heliophysics mission through the outer heliosphere to the local interstellar medium. If you're interested in this study, please go to our website and sign up. And next slide, please, James. So here you're looking at the map showing the layout of the solar system with planets, the heliosphere boundary, and the local galactic neighborhood on a logarithmic scale. Our sun travels in the local interstellar cloud, which is filled with partially ionized gas. The solar wind expanding from the sun moves supersonically away, well beyond the orbits of the planets until it reaches the region where it interacts with the interstellar medium. As a result of this interaction, the heliospheric boundary forms, and you see here the heliopause, the termination shock, and possibly bow shock. So here you see the previous and current missions that brought remarkable discoveries about outer regions of the heliosphere and its boundary. The future mission Interstellar Probe is the heliophysics mission through the outer heliosphere to the local interstellar cloud. We are not going to Alpha Centauri, which you see on the right side of this image, but Interstellar Probe is a pragmatic mission concept to reach distances up to 1,000 astronomical units from the sun, with a lifetime of a mission no less than 50 years. Pragmatic approach implies that technology must be ready for launch by 2030, and with available propulsion technology, Interstellar Probe will achieve escape speed more than twice of Voyager speed. In terms of timescales, for Voyagers, it took about 35 years to get to the boundary region of the heliosphere. With conventional propulsion, Interstellar Probe would explore this region after about 12 years from launch, and in just another 8 years, it will explore the unknown regions in the local interstellar cloud, which we've never explored before. Interstellar Probe will escape the sun and will make the first explicit step to the local galaxy, and this is very exciting. Certainly, there are unique science opportunities for planetary and astrophysics exploration on interstellar probe, enabled by location, which include KBO flybys and looking at early galaxy formation. Next slide, please, James. So the compelling science questions for the interstellar probe mission are: what is the global nature of our heliosphere? How do the sun and galaxy affect the dynamics of the heliosphere? And what is the nature of the local interstellar medium? And in our today's webinar, we are focusing on this third science question about the local interstellar cloud. What lies beyond our heliosphere? Interstellar probe will make the first in situ sampling of the local interstellar cloud properties, including magnetic field, plasma and neutral properties, and composition. Interstellar probe will map hydrogen distribution in the hydrogen wall and beyond, and will make unique detection of interstellar dust grains. And next slide, please, James. Of course, Voyagers 1 and 2 were the first spacecraft who left our heliosphere and entered the local interstellar medium. And Voyagers only explored this region within 30 astronomical units of the from the heliospheric boundary, but already showed surprising and very unexpected observations. Voyagers provided the first measurements of the magnetic field in the very local to the heliosphere interstellar medium, which showed that the direction is not what we expected to see, and moreover, it aligns with the heliospheric magnetic field direction inside the heliosphere. This is very puzzling and surprising. Voyagers revealed that plasma density in the local interstellar medium is by a factor of 20 larger than inside the heliosphere. In the local interstellar medium, Voyagers observed waves that originated near the sun and come all the way beyond the heliosphere boundary. And of course, a lot remains unknown: ionization of the local interstellar cloud, magnetic field direction and magnitude, plasma and neutral particles densities, temperature, composition, and dust properties. Also, one can imagine that the local cloud may be inhomogeneous, creating regions with various properties on different scales. And the sun moving through the local cloud may encounter regions with different magnetic fields, particle densities, ionization, and temperatures. And next slide, please, James. So simulations suggest that different properties of the local cloud produce different global structure of the heliosphere. For instance, ionization. Simulation from early pioneering work show how different could be the structure and size of the global heliosphere for different ionization in the local interstellar cloud. You see the dramatic difference in size and structure of the flows inside the heliosphere between simulations with fully ionized and partially ionized local interstellar medium. The heliosphere boundary appears closer to the sun by a factor of 2 in case of partially ionized interstellar medium. And this is due to the coupling of plasma and interstellar neutral particles in a charge exchange process. And Rosine will talk more about this today. And next slide, please. So recent more sophisticated simulations of the global heliosphere show how different magnitudes and directions of the interstellar magnetic field can impact the global heliosphere structure and distances to the heliosphere boundary from the sun. So for example, on the left image, so-called model 1, with shown direction and magnitude of the interstellar magnetic field, produces sort of distorted heliosphere. And this simulation provides the best match to the Voyager 1 and Voyager 2 measurements of the magnetic field near the nose of the heliosphere. So reduced magnetic field magnitude in the middle image results in a wide downwind region, which is in the tail of the heliosphere, and gives the opposite asymmetries of the heliosphere boundaries. Even more reduced magnetic field and small inclination produces narrow downwind regions, symmetric heliospheric boundary in the nose, and distances to the boundary significantly larger than observed by Voyagers. These simulations and many others demonstrate that conditions in the local interstellar cloud largely determine how our heliosphere look like, what is global shape, dimensions, and implications for particle energization and radiation interplanetary environment inside the heliosphere. Interstellar probe going outside of our heliosphere up to 1,000 astronomical units from the sun will make the first in situ measurements of the local cloud and map its properties with remote imaging observations. And next slide, please. And now I would like to turn a virtual floor to our distinguished speakers today, Seth Redfield and Rosine Lallement, who will talk about the global view of, on the local interstellar cloud and large-scale three-dimensional structure of the interstellar medium surrounding the sun. Thank you.
Thank you, Elena, and thank you all for being here. I've been enjoying these webinars for the last couple months, so I'm thrilled to be able to speak with you today. And I'll be talking about my work on mapping and measuring the properties of this interstellar gas and dust right around the sun. And of course, I do this in collaboration with many colleagues, so I wanted to highlight those. I work closely with Jeff Linsky, Brian Wood, and Hans Mueller. And in particular, I wanted to highlight some of the work done by some Wesleyan students, Hunter Vanier and Fallon Canau, who are off to graduate school next year. So I'll be showing some of their work. Next slide, please. So usually we look at, we start our discussion of the heliosphere and interstellar probe from the inside out. So I just wanted to take a look at it from the outside in and remind ourselves that galaxies, if we put aside dark matter, galaxies are 50% stars, 50% interstellar medium. And so that is the context of the local interstellar medium in terms of the structure of the Milky Way galaxy. And of course, this interplay between stars and the interstellar medium is what drives galaxy evolution and drives the structure of our galaxy. So this is the study of the local interstellar medium provides us the closest environment with which to study detailed phenomenon that are occurring all over our galaxy and in galaxies across the universe. If we zoom in, we see that there are, if we go from 100,000 light years down to tens of light years with the figure on the right, you can see that we reside in an area that has a relatively rich and complex interstellar structure. Well, it's an artistic kind of rendering. It's based on three-dimensional models that we're developing and that you'll see later. Also on that right-hand plot are the location of the nearest stars. And there's two really important things that also occupy this volume of space. One has to do with planets around stars. So Kepler and now TESS are making it clear that planets are ubiquitous, and essentially all stars have planets. Planets are just the natural byproduct of forming a star. And so at the time this figure was made, we identified known planetary systems towards the nearby stars. But indeed, probably all nearby stars have planetary systems associated with them. Also indicated are astrospheres. So the analogy to the heliosphere. All stars also have winds of some kind, and the interstellar medium surrounding those particular stars can create a structure similar to the heliosphere. And in fact, we've identified about 20-ish astrospheres in our local environment. And so I've indicated them as well. And of course, our heliosphere, our interaction with the surrounding local interstellar cloud is going to provide the gold standard by which we evaluate all these other systems, particularly as we start to address questions of habitability, which the astrophysical community and the planetary science community will be working on very intensely over the coming decades. Next slide, please. I also wanted to indicate, and this was a point Elena made as well, and that is that while Voyager is beyond, crossed the heliopause, it is still in this interaction zone between the heliosphere and the interstellar medium. And in order to get to pristine, unperturbed interstellar medium material, you do need to get to a distance of 500, 600 AU or beyond. And that's where the interstellar probe is really exciting to me, because it'll be the first measurements of this pristine interstellar medium environment. And it will provide measurements of the entire structure from inner solar system out to the interstellar medium. Next slide, please. So I wanted to tell you a little bit about how we make measurements of the local interstellar medium and some of the benefits of studying the local ISM and some of the challenges. Because the column densities are so low, this has made studying the local interstellar medium a little challenging and has required us to look at interstellar medium absorption lines in the ultraviolet primarily. And so that's required us to use space-based facilities, for example, the Hubble Space Telescope. So on the right are two sight lines, two stars that we observed, in which we saw local interstellar medium absorption along the line of sight. This is work by Fallon Cano, in which she's analyzing a large sample of stars observed with Hubble. And in these particular examples, you'll notice a couple of things. One is most stars are cool stars. And so if we want to study the local ISM, we're limited to these cool stars that have very little continuum emission in the ultraviolet, but have stellar emission lines. So you see the stellar emission line rising in the spectrum. And then on top of that are these sharp interstellar medium absorption features. The sight line on the right shows how simple the structures can be if you look at nearby stars. In many cases, we find just a single absorber. That might be the local interstellar cloud, the cloud that directly surrounds our solar system. And it allows us to make a very precise and accurate measurement of that absorption. It can get more complicated even for the nearest sight lines. And the example on the left shows an example where there are three absorbers along the line of sight, three clouds. And you can see that they produce distinct Gaussian-like absorption features that we can model. If you go beyond these nearby stars, the interstellar absorption can be incredibly complicated, and it can start to become very difficult using the absorption line technique to extract meaningful measurements of the physical properties of the local ISM. So in many ways, our local environment provides the best opportunity to study that gas and dust in detail. And we can make many physical measurements, such as the temperature and the turbulent velocity from the broadening of the lines, the abundances, ionization structure, the volume density, and some dust properties, which I'll talk about. Perhaps the largest difficulty in this kind of measurement of the local ISM is that it is line of sight averaged. So this absorption, all we know is that it's coming from somewhere in between us and the particular star that we're observing. So it can be difficult to extract measurements of the small scale variation or small scale structure in this material. Next slide, please. So this is a plot of stars in which we have high quality UV absorption line measurements. These are all stars within 100 parsecs. Like I said, once you go beyond that distance, it can get very difficult to extract the absorption lines, and they get very blended. The red dots are from Fallon Cano's sample. The black dots were other measurements, and this may look like there's a lot of dots, but and it was a lot of work to acquire this data and analyze this data. But in fact, this is still quite sparsely sampled. The average distance between these dots is something like 6 degrees. And in some areas, they're still very poorly probed, while other areas have many observations packed in them. So for the dots that are very close to each other, we can identify some small scale structure, and so we know that it exists, but it's very difficult for us to extract those measurements. Next slide, please. This is going to fade into the model of the clouds in the local interstellar medium that we see are present based on these observations. So all of those individual sightlines have their individual spectra, which we've analyzed, and we can then distinguish different structures, different clouds in a local interstellar medium. And we were able to identify 15 clouds. I remember Carl Hylas called this the psychedelic Easter egg. I love that characterization because it is quite complicated, and it just indicates the richness of this interstellar medium environment. So each one of these clouds, you can kind of think of as one of those individual absorption lines components in the spectrum. And it's dominated by the local interstellar cloud, although we don't see the local interstellar cloud in all directions. In directions towards the galactic center, we do not see the lick, and we feel that is because we are right at the very edge of the local interstellar cloud. And I'll get back to that in a few slides. Next slide, please. So that was a two-dimensional projected view of the entire sky in the context of these local clouds. The next step, and something that we're working on right now, is producing a fully three-dimensional global picture of the local interstellar medium and the physical measurements from the spectra mapped on top of that. So the figure on the right shows a preliminary look of a three-dimensional model of the local interstellar medium, where we are looking from kind of the galactic North Pole, you can think of, down at the galactic plane. The sun is at the origin here, 0, 0, and it goes from about -7 parsecs to +7 parsecs. So this is really just our most immediate volume of space around the sun. And you can see the lick is there right at the center. And indeed, the axis is right at the edge of the local interstellar cloud. But we can see these other structures, these other clouds that have distinct properties and distinct kinematics in the vicinity. So this absorption line technique is great for measuring this global picture on a broad brush scale, but it is not possible to get at the small scale structure. So that remains unobserved. So as was mentioned earlier, density variations, ionization variations, dust variations within these clouds is not possible for us to probe with this technique. Next slide. So I wanted to highlight quickly just the dust, because I think that's a particularly interesting component of the InterstellarProbe mission. The way in which we're able to extract some identification of what's going on with dust in the interstellar medium through our absorption line studies is by measuring the missing elements in the gas phase. So we are sensitive only to gas phase absorption, gas phase transitions, and the plot on the left shows the abundances in the gas phase of several elements relative to the solar abundances. So you can see that carbon, nitrogen, oxygen are roughly at the abundances of the sun, but elements like iron and magnesium are way below, meaning we see much less magnesium in the gas phase than we think we should. And presumably that is because there's a lot of magnesium and iron locked up in dust grains. The panel on the right, in the middle, allows us, if we take those amounts in which the missing gas phase elements, we can get some picture of the composition of dust. And so we've done this here with ratios of magnesium, iron, and silicon, and you can see that we can identify olivine type dust in the interstellar medium. And then the figure on the right shows some work we're doing where we're applying a dust model, for example, by Bruce Drain and Joseph Weingartner, where we can take the amount of abundances that we think is in the dust, apply the dust model, and actually measure the number of dust grains with various compositions at particular sizes. So get a size distribution of the dust along various sight lines. And this is, I think, interesting. This is the material in which the Interstellar Probe and other missions may be passing through. So this gives us, you know, a first glimpse of what might be along that path. All right, next slide, please. So the last thing I wanted to touch on is a project that Hunter Vanier and I are working on, which is associated with measurements of the interstellar medium in the direction of the sun's historical path. So as Elena mentioned, it's the interstellar medium environment that dictates most strongly the structure of the heliosphere. And that's because we are traversing different interstellar medium environments on a time scale that's shorter than the kind of solar evolution time scale. So this is work in which we took Hubble observations of a small sample of stars in this very special direction, kind of looking at our rearview mirror, so to speak, at stars in the direction in which we've been traveling. And from that, we can measure the interstellar medium along those sight lines and get some sense of what the sun traversed over the last several million years or so. This is a plot of a couple of those clouds that I mentioned earlier. You've got the Local Interstellar Cloud, the LIC. Again, the sun is right at the origin. The Origin cloud and the blue cloud. These straight lines, diagonal lines, are the direction towards the stars that we're observing. They're nearby, but they're not so close that they would actually appear on this plot. And then the arrows show you the motion of the clouds and the sun. So you can see that the clouds are all moving in kind of the same direction, indicating that these local ISM clouds have a common origin, or they're driven by the same phenomenon. But the solar motion is totally independent of the motion of these interstellar clouds. So if we go to the next slide, we'll be able to see a movie of the last, it starts about 150,000 years ago, hits present day, and then goes about 50,000 years in the future. And so this includes the motion of the sun over this time. This is the black dot. That gray line is the historical trajectory of the sun. And then you can see the interstellar clouds moving. And in our spectra, we identify absorption from all three of these clouds. And so this gives us a sense of how long the sun has been in the local interstellar cloud and when it will leave the local interstellar cloud and what kind of environment will be waiting for us in the future. So again, this is a preliminary model, but we are working on this paper as we speak. All right, next slide. And this is the last thing I want to mention, is the astrospheric observations that I mentioned at the very beginning. One of the stars that we measured turned out to show astrospheric absorption. So we do this by measuring the Lyman alpha absorption. This is work that Brian Wood has been working on for many years. And we model the absorption in the local, in the Lyman alpha profile. It's dominated by the interstellar medium absorption, but given the strength of this very abundant element, we can see signatures of both our heliosphere and of astrospheres. So this is one particular star, GJ173, that shows excess absorption associated with the astrosphere. And I show a model by Hans Mueller on the bottom right for this particular astrosphere. And like I said, the heliosphere is the gold standard with which we use to evaluate this astrosphere, for which we have much less information. So it's really critical that we fully understand the structure of our heliosphere, because we're going to be applying that to our local examples. This is particularly important in measuring the solar wind strengths for these cool stars and these planet hosting stars, because despite the fact that these winds are relatively weak as far as stars go, they're incredibly important and powerful for the evolution of planetary atmospheres. And we've seen that even in our own solar system. Okay, next slide. Okay, I think I'll end it here. I hopefully said all these things at the top are the reasons why I feel the Interstellar Probe is so compelling, because it'll provide us a detailed view of the small scale structure of the abundances and the dust composition and other properties of the local interstellar medium, which is something we just cannot get with these line of sight observations. I'll end it there. Thank you very much. And I'll pass it on to Rosine Lallement.
Hello, everyone. Thank you, Seth. Really nice to see the sun moving out from the lake. In this short presentation, I would like to emphasize the crucial need for measurements of the interstellar matter, the pristine interstellar matter outside of the heliosphere, that means outside the heliopause. And I would like to focus on three different aspects. These aspects correspond to my own interest, I should say, but and they are not the only ones, and they correspond to what I would really like to know about the interstellar medium based on the measurements of an interstellar probe. Next slide, please. I would like to start with this simple movie showing the picture of the ionized media. The solar wind beyond the planets is encountering the interstellar matter, is decelerated by the strong shock, and then is forced to get deflected based by the interaction with the flowing interstellar matter. And this is what I would like to emphasize, is that this is the view, the ionized gas view, corresponds to only to the ionized matter. Next slide, please, James. This view has been beautifully demonstrated by the measurements of the Voyager spacecraft and the 4 consecutive crossings between 2004 and until recently. But the ionized gases who react collectively and has these nice boundaries, I mean, they are not the only player in this game. And next slide, please. What is really important is that the sun is moving in a cloud that is in majority neutral. And the neutrals, they do not react like the ionized particles, they do not react collectively. They react individually and they enter the heliosphere without, at first order, without feeling these interfaces. And if you look, for example, at the number on the left top, I mean, you see that the density of the neutrals is far above the density of the plasma. Next slide, please. This presence of the neutrals is making the whole picture much more complex, and in particular based on a process called charge exchange or electron capture. And the main effect here I show only the charge exchange between interstellar H atoms, which are the major species, and the protons of the solar wind. This process starts with the neutral interstellar atom entering at small velocity in the solar wind, and then charge exchanging with a fast solar proton flowing outside. And just right after the charge exchange, you are left with a fast neutral atom, which is leaving the heliosphere and the solar wind very rapidly, and the slow proton, newly created proton, which is counter-streaming and which will be picked up by the outflowing solar wind, get energized, and becomes a suprathermal solar wind proton, sorry. But this is not the end, and this is only, I show only the first 3 steps, but it is continuing. These fast neutral atoms, they will encounter the proton in the interstellar medium, get charge exchange again, create new neutral atoms which will interact again with ionized flow, and then you can have really many successive charge exchange. And this is rendering the picture, the whole picture of the heliospheric interface and of the heliosphere much more complex. Next slide, please. And this, the presence of the neutrals explains most of the unexpected results of Voyager, and not only Voyager, but more recently the IBEX spacecraft. In particular, and Elena has already mentioned that, the shock solar wind, which is 10 times cooler than expected, and this is due to the presence of the pickup ions. The IBEX ribbon, which is due to consecutive charge exchange, and which is, I like to compare the heliosphere like a gigantic tennis court where the protons and the neutrals, I mean, they go and back. And again, this, the presence of these neutrals and of this charge exchange is probably, in my opinion, explaining some of the remaining mysteries that I have listed here. For example, that the latest state-of-the-art models of the heliosphere and of the interface, they still disagree on the interstellar neutral edge density, I mean the interstellar medium density, the leak density, and the electron density also in this in the leak, and by factors up to 2. Also, there are many unanswered questions like the nature of the bizarre stagnation region that encountered by Voyager 1, the draping of the magnetic field, the existence of a bow shock, the actual shape of the heliosphere, round or asymmetric. There are disagreements. And why mentioning that? I mean, all these remaining, these unanswered questions would probably find an answer if we could have good measurements and precise measurements of the neutral and ion densities and electron densities outside the heliopause and tens of astronomical units in the leak. This would allow to achieve a self-consistent picture of the whole heliospheric system, which is far from simple. And as Seth has mentioned, our heliosphere is an example. And if we understand better this physics of the ionized plasma, we can apply it to other astrospheres, and especially those that are very interesting and harboring habitable planets. So this, unfortunately, the Voyager instruments, I mean, Voyager was a fantastic mission, but the low energy plasma instruments, they were not designed to measure the interstellar medium. And this is why there are still these large uncertainties and why we need measurements with a probe. Next slide, please. The second topic I would like to address, Seth has already talked about the interstellar dust, the cosmic dust. But I would like to emphasize that this the dust is a very important factor in many fields of astrophysics. But all what we know about the cosmic dust comes from indirect measurements. There are no real in situ data of precise data on the interstellar dust, and we are forced to use models. And on the left, you see one of the most recent models for the interstellar dust. And we believe, I mean, the specialists believe, based on all the emission and reddening measurements, that the cosmic dust is made of two main types of grains, the metallic grains in green and the carbonaceous grains here represented in black and white. And this, well, this is from Jones, a recent work of Jones. So in this, according to this picture, there is a large quantity of carbon in the carbonaceous grains and in these small envelopes of the metallic grains. But the very surprising measurement was recently the one with on board the Cassini spacecraft. And this is a result by Altobelli et al. A few years ago. Their instrument was able to measure with a technique of time of flight analysis to measure interstellar grains. They know that they are interstellar based on their trajectories. And they measure the composition of those grains. And the result is that you can see the small bump corresponding to the C+ ion. And they see that there is almost no carbon in the interstellar grains in the heliosphere. Next slide, please. So that was really a big surprise. So there is a need to obtain this ground truth on the cosmic grains. Some potential explanation for this lack of carbon. One explanation could be that maybe in the leak, because it is warm, the carbonaceous grains and the envelopes have been evaporated, completely evaporated, but this is contradicted by carbon depletion in the local clouds. Carbon is missing in the gaseous phase, so carbon must be somewhere, and the only way is in the grains. There is another more likely explanation, is that the carbonaceous grains are probably, well, certainly more tiny, and they are lighter than the other grain that contain iron and nickel, etc. And because the grains are charged, slightly charged in the interstellar medium, and especially when they encounter the solar wind, maybe the charge to mass ratio is deflecting the grains because they are reacting like charged particles, and they are excluded from the heliosphere, and only the metallic grains, the heavy metallic grains, could flow in the heliosphere. But this is speculation. I mean, nobody knows, and there is only one way to get the truth. I mean, it is to test in situ the grain size distribution and the grain composition, and this can be done with a nice interstellar probe. And this would be very important, not only to validate, I mean, to understand the Cassini spectra, but it is important for many fields, as I said, because we need to explain, for example, the reddening curve, the emission spectra of the dust, the polarized or unpolarized, and in many, for example, for the CMB foreground. And there is a need for such a model of the cosmic dust, and only the probe can do that. Next slide, please. The third topic, I will go a little bit farther away, and you will recognize, I will overlap a little bit with the presentation of Seth Redfield. I will mention our galactic corner. Our galactic corner, I mean the local clouds, and the nearby interstellar medium, they consist, they are in a foreground for extragalactic observations. I mean, you cannot, if you look, if you want to look outside the Milky Way, I mean, but you are encountering this foregrounds. And this map is, well, you have seen this beautiful map, is a map made by Planck, the Planck satellite, and it is a sub-millimeter polarized dust emission. And this is dust, and it is this polarized emission by the foreground dust that is that has to be removed if you want to obtain the Graal of astrophysics, which is the B mode of the CMB. Of course, the cosmologists, they don't look in the galactic plane, which is in the middle of this map. They look at high latitude, but you can see on this image that even at high latitude, if you look toward the poles, you still have these shells of dust that you see in pale blue and white. And for the people working on these foregrounds, I mean, there is a crucial need for a better understanding of the structure of these shells and the magnetic field structure to be able to compute the alignment of the grains in the galactic magnetic field and the result, and compute the resulting polarized emission. Next slide, please. Today, toward this goal, we have new results which are really fantastic, and one is the Gaia Mission, and the Gaia Mission is providing distances to more than 1 billion of stars, and we also have today very big detectors and multi-object spectrograph working from ground that allow to get spectra and photometry for a very large billions and even hundreds of billions of stars. No, not hundreds of billions, tens of billions of stars. And so if you measure the reddening, and this is illustrated on this very naive scheme here by the color of the light, if you can measure the reddening of all these target stars, the reddening is due to the dust, the intervening dust between the sun and the target. And if you know the distance and the reddening, you can reconstruct in 3 dimensions by synthesis of all the data. Next slide, please. You can reconstruct and locate the dust clouds everywhere in 3 dimensions. So this reconstruction is on the way. There are several groups working on such reconstruction, and the results start to come, and they will be improved more and more with the next Gaia data release. Next slide, please. And for example, here, this is one result about the location of the dust clouds. So if you look at the left map, this map corresponds to the dust distribution in a plane parallel to the galactic plane within 350 parsec from the sun. The sun is in the middle of the map. The galactic center is to the right, and the direction of rotation is to the top, galactic latitude 90 degrees. You see that, and we knew that, you see that the sun is in the middle of a cavity, almost devoid of dust, very rarefied dust and also gas. And close to the sun, you see a small patch. We don't have yet the resolution that corresponding to the cloudlets just shown by Seth. Here the resolution is on the order of 5-10 parsecs. But this small patch of dust is the counterpart of the cloudlets that just Seth has shown. He has computed the location of the cloudlets based on the gas data, and this is the dust counterpart. On the right, you have a map. I show this map because this is based on the different techniques to get the photometry, that means the reddening, and based on the different technique of reconstruction. And you see that the maps look similar. The location of the big dense clouds, the molecular clouds are the same. And also you have this small patch of dust close to the sun that corresponds to the leak and the G cloud, etc. All the cloudlets around the sun. Next slide, please. Of course, the cosmologists, they are not, and the extragalactic community scientists, I mean, they are not interested in looking in the plane. They want to look to the poles and at high latitude. And this is a cut in the 3D distribution of dust, but this time it is in a plane perpendicular to the galactic plane. So the galactic North Pole is to the top. Again, the sun is in the middle and the galactic center to the right. This time you see the local cavity around the sun, and again you see the small patch of dust clouds, of dust, sorry, close to the sun, I mean the local clouds. And this, when you look at this new map, I mean, you have questions arise, and in particular, are there two bubbles, I mean, two cavities, one in the north and one in the south, like suggested by this map? Up to now, it was believed that there was only one big interstellar bubble. And also these shells, you can see also at about 200 parsec, you can see the shell of dust that are seen to the north and to the, I have added question marks to this shell. These are these shells that are beautifully seen by Planck, and that now can be, the maps can locate. And this is illustrating what has to be removed from the extragalactic measurements, I mean the local clouds and these two shells of gas. Now, why is it important to get measurements with an interstellar probe with respect to this problem? I mean, if you look at the literature and the models for the creation of these bubbles, I mean, they are certainly due to supernovae, I mean, old or more recent supernovae, but the magnetic structure and the nature of the gas in this bubble and at boundaries between the bubbles and the clouds has a strong influence on the charge state of the species in the local clouds. For example, the radiation field would be completely different depending on the age of the bubbles. And so measuring the charge state and the temperature of both the ionized and neutral gas species in the pristine local cloud outside the heliosphere would bring some interesting clues on the scenarios of formation of these bubbles and these local crevasses, as sometimes we call it. And it would help to compute the effect and the foregrounds. Next slide, please. So in summary, about these 3 points, I mean, first, the heliosphere is a fantastic, unique natural laboratory for processes in partially ionized media. And there is a need to supplement the Voyager data by information on the pristine circumheliospheric interstellar gas, because it is majority neutral. And that would provide a ground truth for the heliospheric models. The next topic, I mean, in situ measurements of the dust would be of considerable interest, not only to assess, to understand for example, the Cassini measurement, but also would be of considerable interest for many fields in astrophysics. And finally, the interstellar probe data and measurements of the ionization states, temperature, turbulence, and magnetic field would help establishing the past history of our galactic corner and model the galactic foregrounds to the extragalactic background. Thank you for your attention.
Thank you very much to our panelists. And now we're going to have a real quick question and answer session. So the first question is for Seth, and that's asked by David Gibson. The stars you use to get spectroscopy of the local interstellar medium are variables. How do you know that the sharp absorption features are characteristic of the local interstellar medium and not ejected from those stars?
Yeah, it's a great question. It's the kinematics. So if it was ejected from the star, it'd have kinematics associated with the velocity of that star. And because we see a consistent kinematic structure across the sky, across many stars, that's how we can identify that it's interstellar medium. We do see circumstellar absorption. Beta Pic is a great example where you have an edge on disk. and you do see absorption from that. So it can be tricky, but by and large, it's pretty straightforward.
Thank you very much, Seth. And then the last question, one for Rosine this time, is from William Kurth about the Voyager electron density uncertainty. The Voyager 1 electron densities are very sound with high accuracy. Perhaps you are referring to the lack of understanding with the plasma temperature?
Yes, I think the plasma temperature is not is not really measured. I mean, sorry, I did not catch fully the question. I mean, the electron density, what I have seen looking at the most recent result, I mean, the latest result is mentioning 0.04, centimeter minus 3, which is very close to what corresponds to the cutoff, the famous Voyager cutoff. So it is, to me, it is probably the actual electron density, but the temperature, I mean, is really crucial. And for example, if there is a difference of temperature between the ionized and the neutral gas, that will also help to understand if there is some non-stationarity, and if the event, for example, that has created the bubble has left the interstellar matter is in a non-equilibrium state. So is it, so I don't know if I answered the question, but.
Thank you, Rosine. Yes, for time, we're gonna proceed right now. So that's all the time we have for today. Thank you very much to our panelists, and thank you for attending today's webinar. The next webinar will be on Thursday, August 6th at noon Eastern Time on the possibilities for planetary science and astrophysics, where we will have a panel presentation by several members of the InterstellarProbe team. They are Pontus Brandt, the project scientist, Kirby Runyon, the planetary science lead, Abigail Reimer, the exoplanet science lead, and Casey Lissy, the astrophysics lead. Please visit the InterstellarProbe study website for more information about the study and to view information on future webinars and events. Also, please consider signing up for our listserv under the community involvement section of the website to make sure you are getting the latest information on upcoming webinars and events. Thanks for joining us and have a wonderful day.